Hi everybody, in this video we're going to continue looking at geometric optics, and now we're going to focus on the light that is transmitted when a ray hits an interface. So I'm looking at the summary notes. Over here is our picture. We have the incident ray coming like this from the upper left, traveling down to the right, hitting the interface between materials 1 and 2. So we have indices N1 and N2. We've already talked about the energy that reflects. Oh, and let me mention right now, I should have mentioned this in the last video, geometric optics can't tell us how much of the light is going to reflect and how much of the light is going to be transmitted. It's too simple of a model. We can't answer that question, but we have to use the full-blown electromagnetic wave model where we're looking at the fields, which is what we call physical optics. We're not going to do that in this course. Those equations that tell you how much light energy is reflected and transmitted, you can develop those, again, using physical optics. We do that in Physics 415 Optics, which I keep plugging, right? If you guys want to do that derivation, take that course. Okay, so we're not going to worry about how much light reflects or is transmitted. We're only worrying about directions in this course. All right, so let's get back to the case where we're looking at the light that's transmitted. Now, in order to write down this law in a simple form, once again, I'm going to draw this surface normal. You see it right here. It's already been drawn, that dashed line perpendicular to the horizontal interface. All angles are measured from that surface normal to the rays. In this picture, I have a transmitted ray bending toward the surface normal. Okay, and I just did that arbitrarily. I could have drawn a picture where the ray bends away from the surface normal, right? And we'll look at that case too. In this picture, I chose to draw it so it bends towards the normal. Okay, now that transmitted ray forms an angle theta 2 with the surface normal. Okay, so what is the law of refraction or Snell's law? Here it is right here. The quantity or the product, index times the sine of the angle theta, it's conserved across the interface. So usually we write it like you see there. N1 sine theta 1 equals N2 sine theta 2. Okay? And again, you can prove this using full-blown physical optics, looking at the electric and magnetic field. Physical optics will give you the law of reflection, the law of refraction. It will also tell you how much light is reflected and transmitted. Okay, so let's again concentrate on Snell's law. Now, I'm going to look at two different cases, whether the light is going from a low index into a higher index material or vice versa. Okay, and what happens is summarized right here, case 1, case 2, but I want to look at this in a little bit more detail. So let's look at case 1. And I'm going to go to my notebook here so we can look at this. So case 1, this is N1 is less than N2. Again, I call this going from low index into high index. Okay, now if we look at Snell's law, N1 sine theta 1 equals N2 sine theta 2. Let's just look at this mathematically. If N2 is bigger than N1, then what does that tell us? How does sine theta 1 how does that compare to sine theta 2? Well, if N1 is less than N2, then to keep an equality, sine theta 1's got to be bigger than sine theta 2. Now let's see if you remember your trig functions. If that's true, what does that tell us about the angles, theta 1 and theta 2? Again, just think between 0 and 90 degrees. So if sine theta 1 is bigger than sine theta 2, do I need greater than or less than here? I need greater. Okay, so what does that look like? Again, if I were going to draw that, here's my surface normal. So if I have an incoming ray like this, forming theta 1 right here, theta 2's got to be smaller. So that's got to be like that. This angle right here has to be smaller than this incident angle here. This is theta 1, and this right here is theta 2. I call that bending towards the normal. Okay, so right, if you think about it, if you consider, imagine the straight through direction. So in other words, if this ray didn't bend, whoops, it would go like this. See, the light actually bends towards the surface normal. Okay? So that's what happens in case 1. I would just remember that. Low into high bends towards the normal. Okay? Now, let's look at case 2 over here. And here now we're going to say N1 is greater than N2. Okay, so what happens in that case? Oh, before we do that, I wanted to do this over here in case 1. If we look at typical indices, and I didn't emphasize this when I introduced the index, so I'll cover this now. We know that free space, right, has an index of 1. Air, we're going to say, is approximately 1. Okay, for what we're going to do, we don't have to worry about the difference. Water is a common medium, right, that light encounters. So again, this is not universally, right, always. It's water's index. What I'm trying to say is not always exactly 1.33. It depends what's in the water, what type of water, but we'll usually take 1 1/3. And then, because we're going to look at lenses, and when we talk about image formation, we'll do a lot with lenses. Lenses are usually made out of glass, right, or plastics. And those indices range roughly from maybe 1.4 up to maybe 1.7 or 1.8, depending on the type of glass or plastic. So these are typical index values for typical materials. Now, you can get materials with higher index values, but we're going to mainly consider these common materials. Okay, so the index is not drastically different than 1, but it's significantly different in terms of what happens with the light. Okay, so in case 1, for instance, this might be air going into water, or air going into a piece of glass, or light in water entering a piece of glass. Okay, case 2, this is high index into low index. Now, if you look at this, right, if you go back to, Snell's Law, if N1's greater than N2, then of course sine theta 1, right, has got to be less than sine theta 2, which means theta 1 has got to be less than theta 2. So if we were to draw a picture of that, here's my interface, here's my surface normal, the rays coming in, let's say like that, bending away from the normal, because this angle is theta 1. Theta 2's got to be bigger than that. So this light's going to do something like this, where this angle, theta 2, is bigger than theta 1. I call that bending away from the normal. Again, if you consider the straight through direction, if this ray didn't bend, it would do something like that. Right? The actual light is bending away from the normal, away from that direction. Okay, so there you go. So this might be light in water entering air, or light traveling in a piece of glass entering air. Okay? So again, I would just remember these cases: low index into high index, light bends toward normal, like in the picture. High index into low index, light bends away from the normal. Now, case 2. Let's look at case 2 in some more detail, because something really cool can happen. All right, so there's my original beam, right? And I'm going to just change color. I'm not changing necessarily the color of the light. I'm just changing the color of my marker so we can see this. What if I made a bigger angle? So, in other words, what if theta 1 was bigger? So it came in like that. Well, if you look at the behavior of the sine function, theta 2's got to be bigger. So this light's going to have to bend maybe something like that. Okay? Well, if you keep doing this, right, if you keep making theta 1 bigger, eventually what happens is that theta 2 will hit, according to Snell's law, 90 degrees. The angle theta 1 that gives you 90 degrees for theta 2 is known as the critical angle. for that interface, for those two materials or media. Okay, so by definition, the critical angle is the angle of incidence when theta 2 is 90 degrees. That's neat, but it gets even neater because now the question is, well, what if theta 1 is bigger than the critical angle? What happens to the transmitted light? Well, if you go to Snell's Law, you run into a mathematical problem. Because what will happen is you get an unrealistic value for sine theta 2. It's bigger than 1. Okay, so that can't be. You can't have sine theta 2 bigger than 1. So what's the physical answer to that? The math is telling you you're getting something that doesn't make sense. The physical answer is the light doesn't transmit. So if you come into this interface with an angle of incidence that is greater than the critical angle, none of the light is transmitted. The math tells you that sine theta 2 is greater than 1. That can't be. All the light is, if it's not transmitted, what happens to it? It reflects. So all that light energy reflects, and this is given the cool name of total internal reflection. Oops. Total internal reflection. You'll hear me just refer to it as TIR. Oops, sorry. Oh my goodness. You couldn't see that. TIR. Okay? Because all the light is going to be reflected. Okay, so TIR, let me write it over here in case that doesn't show up in the video. TIR. So what is total internal reflection? It's when all of the incident light reflects back into the incident material. What are the conditions for TIR? Okay, because this doesn't always happen. So what are the conditions for TIR? There are, I would say, the way I'm going to count, there are two. First of all, this can only happen if the light is in a higher index material trying to enter a lower index material. So N1 has to be bigger than N2, but that's not the only condition. And the second condition is that the angle of incidence has to be greater than the critical angle. Okay? Now, speaking of the critical angle, we can actually get an equation for the critical angle. And all we have to do that, I'm going to scroll down to get a little bit more room. Whoops, that's a little bit too much. Let's work down here. Let me go back to the black. Okay, so remember, by definition, when theta 1 equals the critical angle, theta 2 hits the value of 90 degrees. So let's put this information into Snell's Law. So we have N1 sine theta critical, theta 1 is theta c, and then we have N2 sine of 90 degrees. Well, what's the sine of 90 degrees? Yes, it is 1. So there we go. The sine of theta critical is going to be N2 over N1. So if you want to figure out the critical angle, all you have to do is take the inverse sine of N2 over N1. Okay? And I think you can see mathematically why N1's got to be bigger than N2. Because mathematically, if N2 were bigger than N1, you would have the sine of the critical angle is bigger than 1, which can't be. Okay? So what are the two conditions for TIR? First of all, it can only occur if N1 is greater than N2, light's going from high, trying to get into low index, and the incident angle is bigger than the critical angle. Okay? And something interesting, even though geometric optics doesn't show you this, I'll mention it. Let's say that you're starting like with what we call normal incidence. So normal incidence would be theta 1 equals 0. Right? So if theta 1 equals 0, that light, come up here, theta 1 equals 0, that light's coming straight down. Okay? According to Snell's law, theta 2 has got to be 0. That's the only possibility. So that transmitted light's going to go straight through. That's going to give you the most transmitted power, normal incidence. As this ray starts forming a larger angle theta 1 with the surface normal, as that angle theta 1 gets bigger and bigger, you're getting less transmitted light and more reflected light. And once you hit the critical angle and beyond, all of the light energy is reflected. Okay, so I thought I'd just mention that. Okay, so that summarizes Snell's law, and we've also talked about the phenomenon of total internal reflection. Okay, now the homework problem that goes with this section, the collected homework problem, is 1A, and it deals with an optical fiber modeled with the simplified geometric optics. And I just wanted to mention that we do rely on total internal reflection for light traveling in an optical fiber. So we can have the light go very long distances through the optical fiber. And real briefly, what happens there is in the optical fiber, if I were to draw a cross section, the fiber itself is cylindrical. The inner cylinder, very, very narrow diameter on the order of microns. But this cylinder you can think of as having index N1, and it's going to be surrounded by a cylindrical shell. So in cross section, it looks like a sandwich. But really, right, it's a solid cylinder piece of glass, and then surrounding it is this cylindrical jacket, which is a cylindrical shell. Okay, so the cylindrical shell has an index of N2. So what happens is we inject the light into the fiber. So here comes the light. Let's say it's coming like this. And we're going to do this with a laser. Now you see, that's the first surface normal is that vertical interface. You can think of this index out here, let's call it N0, right? So maybe that's air, so that would be close to 1. So you're going to get a refraction when the light enters the core, because N1 is going to be bigger than N0. So this is going to bend towards the normal. So it's going to bend something like this. And then it's going to come down like that. Okay? Now, here's another interface right here. See this horizontal interface? That's the interface between the core and the cylindrical jacket. So here's the surface normal for that interface. So this ray right here, it's going to form that angle, theta 1, with this vertical surface normal. So what you want to make sure of is that theta 1 is bigger than the critical angle for this fiber. So N1 is going to be bigger than N2. You're going to have two different types of glass or plastic in a cheaper fiber where the light doesn't have to travel as far. So geometrically what happens is all of this light energy is just going to reflect and go like that. Now, according to the law of reflection, that angle is the same as theta 1. And now, right, you're guaranteed for this interface right here. There's the surface normal for the next interface. Whoops. You're guaranteed. I just made that go away. Can I get it back? I can't get it back. Let's see if I can get it back. Oh, there you go. Got it back that way. The good old Control Z. Okay, so there's you're guaranteed that this this angle right here is the same as the original theta 1, so you're going to get TIR off of this interface, and I just made it go away again with my giant finger, and so then this ray, right, is going to go like that, where that angle is going to be the same, and this light in the geometric model just zigzags through the fiber. Okay, so you're going to analyze this in problem 1A. I'll talk more about that problem when we meet in class. Okay, but this is the general setup. So if you don't come to that class, this might help you start that problem. Just realize that there are two refractions that are occurring. The first refraction is at this interface, and then we're looking at this, I should say there are two interfaces because there's not we don't want a refraction at that second interface, but there are two interfaces you're going to have to look at. And there's geometrical relationships between all those angles. Okay, so there we go. I'm going to stop now. And in the next video, we'll talk a little bit about dispersion, one of the consequences of refraction, and the fact that the index is not a constant if you look at different frequencies. All right, goodbye.